In the intricate world of high-voltage transmission systems, such as 400 kV and 220 kV, the design favors efficiency and optimization over redundancy. The absence of a neutral conductor is rooted deeply in the principles of three-phase power. Each of the three phases, red, yellow, and blue, works in harmony, balancing loads naturally. When these loads are balanced, the currents effectively cancel each other out, resulting in a net current of zero. This characteristic makes a separate return path, or neutral, entirely unnecessary, echoing the elegance of simplicity in engineering design. Continuing with this streamlined approach, including a neutral wire in high-voltage transmission lines would be an exercise in excess. The structure of the lines would become more cumbersome and financially burdensome without providing any discernible benefits. The conductor would add weight, necessitating stronger tower designs and superior insulation, further increasing costs. In this delicate balance of design, each component is meticulously calculated to ensure efficiency and safety, allowing the system to operate with minimal losses and maximum output. The role of transformers at generating or transmission stations is equally pivotal to this discussion. Often configured in a star-grounded arrangement, these transformers provide stability by grounding the star point, effectively negating the need for a neutral wire throughout the transmission network. Grounding serves as a fail-safe, allowing fault currents to safely travel to the Earth in instances of imbalance, ensuring a swift response to potential hazards, all while fostering a robust system. When delving into distribution systems, the presence of a neutral conductor becomes palpable. Through step-down transformers, transitioning from higher voltages to the familiar 400V or 230V seen in homes and businesses, the necessity for neutral arises to accommodate single-phase loads. At this juncture, the neutral point, crafted from a star connection, provides the essential return path for electrical flow. It becomes part of a well-orchestrated dance, feeding power to our everyday lives with precision and reliability. Transmission systems operate predominantly using three phases due to efficiency and balance. Power travels across transmission lines in waves, like a synchronized dance, allowing large amounts of electricity to flow seamlessly. This three-phase arrangement minimizes energy losses during the long journey from generation sources to distribution networks. Similar to a streamlined vehicle cutting through the wind, three-phase lines are designed to optimize performance while reducing operational costs. The absence of a neutral conductor is intentional, driven by the principles of high-voltage transmission. In a balanced three-phase system, the currents in the three conductors are equal, effectively canceling each other out at the neutral point. This balance means that the neutral wire becomes redundant and unnecessary during optimal operation, simplifying the design. Consequently, relying on a grounding system affords adequate safety and protection from faults without needing an additional neutral conductor, which would serve little purpose for the high voltages involved. Upon reaching the distribution end, the dynamics shift slightly. Here, the neutral is created through star, Y, connections from transformers, which provide a necessary path for unbalanced loads. Picture the transformation at this juncture, where a grounding point stabilizes the system, allowing the flow of electricity to be safely distributed among users. This pivotal transition from the absence of a neutral in transmission to its presence in distribution showcases an efficient and well-designed electrical network that prioritizes safety, efficacy, and economic feasibility. In essence, high-voltage transmission systems, like the 400 kV and 220 kV lines, do not incorporate a neutral conductor to harness the benefits of a balanced three-phase system. By eliminating unnecessary components, these systems thrive on reduced operational costs, increased efficiency, and enhanced safety measures. Imagine vast stretches of land covered with towering transmission towers, effortlessly sharing electricity across great distances. With the available grounding techniques, the systems become resilient, ensuring reliable electricity delivery without overcomplicating the design. The transmission and distribution of power represent a remarkable feat of engineering and planning. As electricity journeys from generation stations through expansive grids, it transforms lives and powers modern conveniences. The thoughtful design elements, including the effective use of phases and grounding solutions, pave the way for a robust and reliable power infrastructure. Each element harmonizes like the components of a finely tuned orchestra, delivering energy precisely where it is needed and empowering our daily lives with each passing moment.